Okay, so all of my chemistry class is on video instead of just half of it. So let's go ahead and let's go over it. So like how you do normally in class, let's go ahead and let's get out your homework so that way we can go ahead and go over it. So you had 2 questions on page 61. Remember, these were due Friday, but we didn't have time to go over them on Friday, so we'll go over them now. And then you also have those 3 questions on page 65. Also, don't forget, I need your lab report sheets emailed to me today. So if you didn't turn in lab 7, you know who you are. Who didn't turn it in on Friday because it wasn't quite complete yet. So you know who you are. So make sure that you take a photo of both the pages for lab 7, email them to me today. And then also remember lab 8 is due today as well. So take a photo of the front page and then the back page. Remember, it's only just that question 1 is due on the back page. I need both those pages today. Make sure you take a photo of them or ask your parents to take a photo of them and then email the photos to me so I can grade them. So don't forget, I need lab 8 today and then lab 7 if you didn't put it in on Friday. Let's go over your homework. So go ahead and get that out. Alright, number 1. State the postulates of the kinetic theory of matter. This is on page 61. So, state the postulates or the parts of the kinetic theory of matter. So, there are 5 parts to it. So, number 1, gas molecules are in constant, rapid motion. Number 2, gas molecules undergo elastic collisions. And we'll talk about what that means later. Number 3, the kinetic energy of a gas molecule is directly related to temperature. Number 4, gas molecules are very far apart and have negligible volume compared to the volume of the gas. Number 5, gas molecules have negligible attractive forces between them. We'll talk about what that means later. Number 2, what term refers to a gas that exactly obeys the assumptions of the kinetic theory? We call it an ideal gas. Alright, number 1 through 3 on page 65 now. How many millimeters of mercury, torr, how are millimeters of mercury, torr, and atmosphere related? Hopefully you wrote there are 760 millimeters of mercury equals 760 torrs, and that all equals 1 ATM. We'll talk about the reasons why, so don't worry about it if you're confused. But that's the relationship. That millimeters of mercury and torr are the same size. You need 760 of them to equal 1 atmosphere or 1 ATM. We'll talk about the reasons why later. Number 2, what is standard pressure in torr? 760. So kind of like what I just said, you have standard pressure or standard atmospheric pressure. You have 760 torrs. And then number 3, what is a manometer? So it looks like manometer. You technically pronounce it manometer. So make a note for that. So what is that? A manometer is a laboratory device that measures gas pressure as a difference between mercury levels between the arms of a U-shaped tube. So that's just one way of explaining it. Alright, let's go ahead and let's put that away for your homework. And then go ahead and get out your textbook. We haven't gone over any new material because of your tests on Wednesday and because of the labs. So now we get a fresh start and start talking about gases and the gas law. So as you can tell from my photo, we use these mainly with objects that rely on gases, but you use them as day-to-day objects as well. So we associate these with balloons, and that's an easy application. But there are many other properties of gases in particular. Like for example, whenever you breathe, you're breathing in a gas, and then you're breathing out gases as well. Now your book points out that the air we breathe is a homogeneous mixture. Do you remember what homogeneous means? Now remember, I know we haven't talked about it directly, but chemistry builds, so you need to make sure that if we use a term previously, you want to still keep up with it, because otherwise you're going to get kind of lost. Remember, homogeneous is something that is completely mixed, and you can't really tell until there's individual parts for it. So a homogeneous mixture of gases, we have predominantly oxygen and nitrogen in the air we breathe. There's also helium, there's also carbon dioxide, there's other gases in there. But it's not like you have a pocket of oxygen in the air and then a pocket of nitrogen in the air. They're all mixed in. It's all homogeneous all together. All gases are completely miscible. So make a note of that on page 60. So miscible, that means able to be mixed. You don't have a gas of one type chill out in one section of a room and then have a different gas chill out in a different section. They're all mixable all together, which is good. So in my chemistry class, I don't have to worry about hopping from pocket to pocket of oxygen in the room. All the oxygen spreads out from each other evenly in the room as best as it can. So all gases are miscible or able to be mixed, and they diffuse or spread apart very rapidly. Gases want to spread out from each other as much as possible. So if I were to go ahead and spray Lysol in one corner of the room, and I were to stand there and spray it, Lysol would not just chill out in one section over my desk. It'll start to spread out throughout the whole room. And if I were to spray it, Mr. Nadasky would eventually smell it, probably over in his room. Or, like on this past I believe it was Thursday, whenever I lit things on fire in physical science class, the smoke or the smell stayed in the room as best we could, but if you were in the hallway or other classes, you might have even smelled it then, because the smoke wants to diffuse, or the smell wants to diffuse as much as possible throughout the school. Alright, the book points out gases can also flow from one place to another. They're a type of fluid. Think of fluids mainly for liquids like water or coffee or soda. But a fluid is just an object that can just move. So a gas and liquids are both fluids, so they can flow or move about. Gases have mass. Gases can be readily compressed because their molecules are very far apart. Gases expand and contract with temperature changes, and they completely fill any vessel of any shape into which they are placed. So again, working with balloons is the easiest way to show this type of thing. So gases have mass where they take up space. You want to think of it that way. So if you were in class, you would get a balloon. Sorry, you're not in class. So if you have these at your house, your mom or your grandma or your aunt, or whoever you're watching this video with, they might have some at their house. So if you want to go pause the video and go ask them for one, you can. But I'm going to go ahead and blow up this one partly at least. So this is a little bitty balloon, but it'll work for it. So you can see how it's taking up mass. It's taking up space now on the inside of my balloon. So my balloon has mass, or has something on the inside. I don't want to accidentally pop it. The gas, they can also be readily compressed. So if I wanted to, I could squeeze my balloon and shift my gas from one side to the other. Now eventually, if I were to keep blowing up my balloon, I'm taking air from my lungs and I'm putting it into this balloon. Now it's not just carbon dioxide on this side. No, we say we breathe out carbon dioxide, but it's still a mixture of gases. So it's not just pure carbon dioxide in this balloon. There's other gases inside of it. But if I were to keep blowing it up, I could compress or try to fill up this balloon as much as possible with gas. Now eventually this poor balloon can't hold anymore. So what will happen to my balloon if I try to compress too much gas on the inside? You're right, it'll pop. And so because of that, I have to be able to give a little bit, but I could blow up this balloon more if I wanted to. So my balloon is large now. I put in another lungful of air onto the inside of it. So I'm compressing or pushing my gas molecules together. I also notice that my balloon has more resistance now, and I don't want to accidentally pop it. But it's where the gas is. They are now being compressed on the inside of it. So the gas molecules, they are very far apart, but I can force them to be closer together on the inside of the balloon. Gases expand and contract with temperature changes. So if I were to take my balloon, seal it off, and put it in the fridge, my balloon would be slightly more shrunk tomorrow because the gas molecules have lost energy. So they would come in a little bit closer together. If I were to stick this in a really warm area like my car and let it sit there for a long period of time, it would expand slightly because my gas molecules have more energy and they want to spread out more from each other. They will also completely fill any vessel of any shape to which they are placed. So I don't have the gas just chilling in on one side of my balloon. I have sealed off the bit of my balloon because what would happen if I would let go? Well, the gas would all escape out because the gases would want to spread apart from each other. So if I were to shift my fingers down, the gas is now trying to spread out into that section of my balloon as much as possible. You don't see just an awkward flat portion. Now, it is a little bit looser in that section because it's a thicker area, but it's trying to fill up my balloon as much as possible. I don't have just half the balloon filling up with air. It's trying to fill as much as possible. Now, if I were to let go, I'm going to make sure I hold on to it, that the gas will spread out as much as possible because it doesn't like being together. So we can know that they will completely fill any vessel of any shape to which they are placed. So those are just some of the different properties of gases. Alright, so kinetic theory of matter. A gas is greatly affected by both pressure and temperature changes, both of them. We see this more with tires on a car. Your mom might have noticed, or your dad might have noticed that the pressure of the tires has adjusted in different temperatures, or with different types of pressure that's pumping into it with like a bicycle tire. So a gas is affected by pressure. So if you ever pumped up a bicycle tire before, you'll know the first couple pumps aren't bad whenever you're pumping it up, but the more you pump or push air into the tire, the harder it gets. And that's because you're pushing those gas molecules close together, and they don't like being close together. So the pressure, how much you put into it, or the pressure on the outside of the container greatly affects them. Also, temperature changes. Your mom with the fluctuating temperature again right now, with the temperature of the weather outside, your parents might have gone to go get the tires checked because the low pressure gauge might have come on or gone off. That's probably the reason why they might go get them adjusted, because the temperature outside affects the pressure of the gas molecules on the inside of your tires for your car, and you have to get that adjusted, typically in the winter time. So that way, as you have those colder temperatures, the gas molecules will get slightly closer together, and so it might trigger the low pressure warnings where your parents have to go put more air in your tires. If you don't put air in your tires and you keep driving around like that, your tire can break. So that's probably the reason why you want to make sure you get proper pressure on the inside of your tire. So we don't really worry about this with solids or liquids, because since solids or liquids are more or less locked into place, like a solid, because they're solid, they don't really shift around that much because of temperature changes or pressure. There is some very, very, very slight shifts, but it doesn't really matter. For a liquid, because they're already next to each other and they're flowing, again, because there's very slight temperature changes or pressure, there's some very slight kind of shifting, but it doesn't really matter. Gases, it matters a lot, because the gases want to spread out each other as much as possible. So you can push them together with pressure, or they'll get closer together because of temperature changes, or they want to spread out because of temperature changes. That's the reason why for gases you need to know the pressure and the temperature. Not necessarily for a liquid or solid, but for a gas you do. So your book points out, if pressure increases, the molecules are forced closer together and they collide more into each other. Or if you have the temperature increasing, in the same idea. They might not be closer together, but they have more energy, so they want you to spread it out because they're moving faster now. So that's why if you have more pressure or if you have an increased temperature, they want you spread out from each other as much as possible. Alright, so again, just make a note that you have to talk about pressure and temperature if you're talking about a gas. So your book points out the relationships of pressure, temperature, and volume, and has been described in what are known as the gas laws. So again, this is a chapter about gases and gas laws. There's a lot of equations in this chapter, as a side note. So the observed behavior of the gases, the observed behavior of the gases described in the gas laws can be explained in part by the kinetic theory of matter, so also known as the kinetic molecular theory. So there are basically 5 parts to it. You want to know the 5 parts, and again, balloons are the easiest way to see this. But just make a note, the kinetic theory of matter, or the 5 different parts for it. Alright, part number 1. Gas molecules are in constant, rapid motion. Remember this physical science, we said molecules are always moving, so that's the idea of the kinetic theory of matter. Gas molecules are in constant, rapid motion. They will move in a straight line until they hit something, and then they will bounce off that, and then ricochet. So, just make a note, gas molecules are in constant, rapid motion. They move in straight lines until they collide with another, or if it's solid or liquid, such as the container's wall. So if I were to blow up my balloon, the gas molecules on the inside are basically moving all around on the inside, but it's the balloon's wall that's keeping them from escaping. Number 2, gas molecules undergo elastic collisions. That just means whenever they hit an object, they don't lose energy. So again, this is part of the kinetic theory of matter. In real life, if you were to run into a wall, you would lose energy because some of your energy would be transferred into the wall in sound waves and pain. But with the gas molecules, we say, okay, they undergo elastic collisions where they hit an object and then they just bounce right off. They're ricocheting and they're not losing energy. That's an elastic collision. The kinetic theory of a gas molecule is related directly to temperature. We'll talk about the reasons why a little bit later on, but basically the energy is related to the temperature. We can associate this with the energy in food. So if you have a higher temperature or there's more energy in the food, then we would say that the food is hotter. So same idea. Or if you have a colder temperature, there's less energy outside, or less energy, like if you go outside, there's less energy because it's colder, so there's less energy in the air. So you can think of it that way. We'll talk a little bit more detailed later on though about it. Number 4, gas molecules are very far apart and are negligible in volume compared to the volume of the gas. I'm going to blow this up again so you can visualize this one a little bit better. Alright, so they're in constant rapid motion on the inside of the balloon. They are moving around in those straight lines until they hit either each other or the side of the balloon, and then they'll bounce or ricochet back. Remember, they undergo elastic collisions where no energy is lost, and they are directly related to temperature. This air is probably the same temperature as the air in the room now. Now, once it's on the inside of the body, it's a little bit warmer, but now that they're outside my body, they're probably about the temperature of the room now. So, they are very far apart and are negligible in volume compared to the volume of the gas. Alright, what does that mean? That means whenever you're talking about the volume of the gas, I mean the entire container. I'm not talking about the itty bitty little volume of the carbon dioxide, oxygen, helium, or nitrogen on the inside of this balloon. If I'm talking about the volume of my gas sample, I mean the entire balloon altogether. I'm not talking about just the oxygen or just the carbon dioxide. So that's what it's saying. So the gas molecules are very far apart and they're negligible, or don't really matter in volume compared to the volume of the whole gas altogether. So that's what the fourth one is. And then the fifth one, gas molecules have negligible attraction between them. So remember how you have the cations and the anions, or you have the ions that have positive and negative charges. Well, if you have a positive gas, slightly charged gas, and a negatively charged gas, they should be attracted to each other. Now what she's saying with the kinetic theory of matter is saying, okay, that they are so small and so far apart that they basically don't have an attraction to each other. Alright, in real life, they do have a slight attraction, but they're saying, okay, for our theory, in order to explain what we see for gases, we're going to just say that they have a negligible attraction or they don't really have an attraction between them, that they will just go right by each other and not really interact. Alright, I'm going to let this go because I got to use this hand. Okay, put that back down. Alright, so your book points out that the kinetic theory is literally a moving molecules theory. Gas molecules are continually moving around and colliding with each other with other surfaces. Now, in real life, gases don't really follow every single part of this theory. But we have to come up with an explanation over what we see gases do and how they react. And this is our best theory at the moment. So even though we don't really have a lot of gases that follow this perfectly, it's one of those, this is the best guess at the time. We might not understand everything about it, but this seems like it's accurate, and in most cases it works, and on the day-to-day level it lets us explain why we see gases do what they do. So that's why we use this theory. So it's one of those where it might weird you out to think, well, it's not perfect all the time. Again, science is not a perfect thing where we know every single thing all the time. Science is constantly learning. So in 20 years from now, we might have a different theory where they've changed it slightly, and your kids might come home and talk about the updated kinetic theory of matter where it's slightly different. And that's okay. This is the best explanation we have at the time. So your book points out a gas that exactly obeys the assumptions of the kinetic theory. We call it an ideal gas. It's perfect, or it's ideal. It follows the kinetic theory of matter. Speaking of that, the gas that exactly obeys the assumptions of the kinetic theory is an ideal gas. Your book points out, in real life, we don't really see gases obey every single part of it all the time, but on a daily level, this is a good explanation, and it works for what we see on the day-to-day level. So, your book points out it's a good approximation or a good explanation over what we see gases do. Gases are going to do what they do whether or not we understand it. So, God said in laws of nature, and they will work whether or not we understand why they work. So this is a good explanation over why we think it works this way, even if we're not entirely sure. Alright, your book introduces in concept in chemistry the concept of probability. Normally I would call on Ethan or Chris to read this, but they're not here because I'm alone. But so because of that, I will read it. So follow along in your book and we'll help explain it. So the gas law is the relationships between variables, measurable properties that may be varied. Pressure, volume, temperature, and the amount of gas or moles are all variables. Each of the simple gas laws deals with the effect of one variable on another while keeping all the other conditions the same. If we wish to study the effect of a pressure on a gas volume, for example, all other conditions, variables, must be held constant, or we could not unquestionably attribute the observed results to pressure variations. The same is true for the other possible variables. In the gas law, the relationship between volume, temperature, pressure, and the amount of gas are proportional relationships. Quantities that are proportional are related to each other by multiplication by a constant, a number that is fixed value in a given situation. Alright, there are two different types for this. A direct proportion is a relationship in which the value of one variable depends directly upon the value of the other variable. The expression, and it gives it to you, is an example of a direct proportion where the x is equal to the constant k times the variable y. If y triples, x must also triple. If x is half, y must also be half, so the ratio of x divided by y stays the same, remains equal to the constant k. In a direct proportion, a change in one variable brings about a similar change in the other variable. Alright, what's that mean? A direct proportion means that if one of them goes up or increases, the second one must also increase. They are directly tied together, or they are directly related, if you think of it that way. So, direct proportion. If one goes up, the other one must also go up. If one goes down, the other one must also go down. So they are tied together, if you think of it that way, or they are directly related. Alright, an inverse proportion is a relationship in which the value of one variable depends upon the reciprocal or the inverse of the other one. And then mathematically, and it gives it to you. In this case, if x is doubled, y must be half, so that the product xy remains equal to the constant. Similarly, if y is tripled, then x must decrease to 1/3 of its original value. Thus, in an inverse proportion, the change in one variable brings about an inverse or reciprocal change in the other one. Alright, so what's this mean? That if you have one of them go up, the opposite has to happen, or the inverse has to happen. So it has to go down. So they're opposites from each other, or the inverse of each other. If one goes up, the other has to go down. Alright, so that's the two major proportions. So direct proportion, they're moving the same way, in the same direction. Inverse proportion, they're opposites. If one goes up, the other one must go down. Alright, so do you make a note of that? The 5 different parts of the kinetic theory of matter, an ideal gas, and then direct proportion, and an inverse proportion. Alright, anyone have any questions? Well, I can't ask that, I forgot, because you're all here, you're not here. But if you have a question, be sure to email me, so that way I can hopefully email you back as soon as possible. Alright, moving on then. Alright, understanding gas and pressure. Alright, you look at this diagram, and then here's your first two equations for this section. Your first one has to do with kinetic energy, or energy of motion. This is whenever you have a moving molecule, how much energy does it have? Kinetic energy has to do with the idea of the energy of movement. So, your book gives you the equation. Let's go ahead and let's go over this. I moved my chalk. You need to stop doing that. Alright, so this first equation, Ke, or kinetic energy, equals 1/2 mv squared. Okay, so this is the exact same equation that hopefully you remember from physical science either a year or two ago. So let's go over this. So M stands for what, typically? Hopefully Chris, Ethan, Jamie, and Quentin all said mass. V stands for velocity or speed. We're going to talk more a little bit about that later on. But just make a note that V stands for velocity. And then this is just 1/2. Or you could divide, or you could type it in by you can either multiply by 0.5 or divide by 2, so whatever way makes it work better for you. Now keep in mind, you have an equation like this where you have an exponent. What do you do first in the second equation? Go put in the order of operations in algebra. Trying to look around the bar and smack down in the center of my angle. Good job. Well, hopefully you said okay, that you multiply by the exponent, or this time you square it first, and then you multiply everything else in it, or divide if you're dividing by 2. Alright. So, working out just kind of like a practice problem. Let's say that for this particular substance, that you have an object that has 50 grams of mass, and it's moving at 5 meters per second squared. Alright, can't write and talk at the same time. Alright, so if this is the mass, this is the velocity, how do you solve this? Okay, remember, first things first, you want a 5 squared, so 5 times 5, or if you type it in your calculator, 5 raised to the second exponent. 5 times 5, or 5 squared, multiply it times 50, and then divide by 2, or multiply times 0.5. What do you get? Hopefully you got 625 joules. Remember, joules is the unit for energy, so kinetic energy, or joules, is the unit for it. So, your book doesn't tell you this on this page, but I'm telling you as your unit, so write it off to the side. I think your book tells it to you a little bit later on. But just make a note that the SI unit, or your unit for energy, is joules. So, again, if you ran into trouble solving this, either email me or try to contact me. I think I have my phone number. I think your parents, some of you have it. So just make sure you either have them call me, or we can set up a phone time, so we can have a Zoom session over some of the math, because there's a lot of math in this section. So the answer to this one now, 625 joules. We're ignoring sig figs for right now, just so you can just check to make sure that you understand the process over how to solve this. Alright, so that is the equation for kinetic energy. What is it saying as well? Since this one is energy, or the speed of the molecule, if you have an object that has more speed, or it's at a higher temperature, it'll start to move faster. So we say if you have a higher temperature, then you have more kinetic energy, and that's how they are related. So, speaking of the higher temperature of the gas, the greater the average kinetic energy of the molecules in the gas, and the lower the temperature, the lower the average kinetic energy of the gas molecules. Since this is velocity or speed, if I have the objects that are moving faster, they have more energy because they have more motion. So that's why they are related in that regard. Alright, pressure, if you're talking about the inside of a container, this is the second equation that you need to know. This equation is pretty straightforward too. So this equation is showing you a pressure. So P for pressure equals the force divided by the area, or unit area. So this one is just a simple fraction. So hopefully you know how to solve this type of equation, but if you don't, you should email me. So your book points out that each individual collision does not produce a noticeable force, but if you have a bunch of molecules on the inside of your balloon or on the inside of your gas, they can produce a lot of pressure on the inside of the balloons. Even though each little gas molecule isn't very large, altogether they can work together to push out your balloon. So that's where you have pressure on the inside of your tire or on the inside of a balloon for it. So just make a note that pressure is defined as a force or push per unit area. So the first time you've seen the word force in your textbook, just make a note for it. A force is a push or a pull per unit area. Alright, so let's just say though, for practicing with this equation, so let's say you have for the force 16 newtons over a, we'll say 4 meters squared area. So you have 16 newtons divided by 4 meters squared. So hopefully you can figure out, okay, 16 divided by 4 for this one, it would be 4 pascals. So just make a note. I think your book tells you as well, a little bit further down underneath the balloon picture. Now the SI unit for pressure is the pascal or PA. It's 1 Newton. This is the SI unit of force per square meter. Just make a note that newtons is the unit for force. We don't get a whole lot into it, but just making sure that you know newtons is the unit for force, where pascals is the unit for pressure. So make a note for both of those. So again, if you have a question about how to solve this equation, sure to email me, but it'll come with time. But these are the first 2 equations that you need to know for this section. There's a bunch, so make a note for it. Alright, book points out this gas molecules move randomly and spread out uniformly in a container. The pressure they exert is the same in all directions, so it's not like there's more pressure at the top as opposed to the bottom. The gases are spread out as much as possible, so they're all pushing back against the sides of the container as much as possible. So, just make a note for that. Typically, whenever we're talking about a pascal, that unit of pressure, we don't mean one individual pascal. A pascal for pressure is approximately the pressure of a 6-gram sheet of typing paper on the surface of an object. So if I were to take a piece of regular printer paper, lay it down on this counter, that is how much a pascal unit of pressure is. And that's really small. So typically we use kilopascals. So hopefully you remember what kilo means, or the K. So I can't ask anyone, but hopefully if I were to ask you what does the kilo stand for, hopefully you said 1,000. So we talk about, instead of talking about 1 pascal, we talk about kilopascals, 1,000 pascals at once. So that's our major unit for it. Alright, so talking about how do we measure gas pressure then. Alright, the first major way is we can use a barometer. So, if we're talking about our atmosphere, since we have gas all surrounding our Earth with our atmosphere, which is good, we need it, then we can measure it with a barometer. So make a note of the barometer, and that's the device we use for it. This one is a very early model. Your book has this picture at the top of the page on page 62. So, it was, the mercury barometer was invented by, alright, I'm going to try to say his first name, but I'm not Italian. So, Evangelista is how you're supposed to say it. It looks like Evangelista is how it looks. So if you want to remember it that way for quizzes and tests for spelling, okay, just make sure. So Evangelista, Jaliste is how you're supposed to say it. So make a note for that. That's his first name. But Torricelli is his last name. So that's the important part. So make a note. Torricelli. That's the last part, and that's the part that you really need to know. So, he was measuring it with mercury. Now, keep in mind, we do not use mercury today. Now, in some weather stations, they still use a mercury barometer, but on a day-to-day level, we don't use a mercury barometer. What he did is he took a tube of mercury, filled it up with mercury, and then capped the end of it, and then put it on the inside of another container. So, if you were to use a straw for this, what he did was he basically filled up the tube with mercury, capped it, stuck it, and then inserted it into the rest of his mercury container and then let it go. So that was the basic idea over what he was doing for it. Again, do not do this in real life. So, what he did, I'm going to try again to draw it, but you gentlemen remember, and ladies, Jane, remember, I'm not a very good drawer. I'm trying to do this quickly as best as I can. So, he had a container, he had his mercury tube on the inside. Well, whenever he did that, the mercury column would fall slightly on the inside of the tube. So you still have mercury on the inside with the insertion of the tube in his container of mercury. But he noticed, okay, all of it doesn't go swoosh into his container. Now this up here is not gas. Because he had it filled up with mercury, and because he flipped it over and then immersed it, that all of his mercury container was sealed. So whenever he did that, there is no gas trapped at the top. That's a vacuum. So make a note of what a vacuum is. I think your book has told you previously, but just in case, make a note of what a vacuum is. There is no air trapped in this section. It's just an area of empty space, so a vacuum. So nothing's pushing the mercury up there. So Torricelli noticed, okay, my mercury is remaining suspended on the inside of my tube. Why is it not all of it falling in my container? So he was studying basically air pressure, noticing, okay, there's still air pressure pushing on the outside of my tube. So the atmosphere is pushing down on mercury on this level, but there's no air pressure up here. There's no gas there. There's no air because this is a vacuum. So the air is pushing down on either side. So it's keeping the top of the mercury level. So that way the mercury is basically rising up in here and is basically sitting up in there because there's nothing to push it down up at this point. If he were to open up the top of his tube, now there's air pressure pushing down on the inside of the tube as well, and then the mercury would fall at that point. But because with his tube, since it's sealed off and there's no gas on the inside, since this is a vacuum, the mercury can basically stay suspended like that because the air is pushing down on either side, and so it's keeping the outside portion from raising anymore because it's pushing down. So it can have the mercury stay suspended or raised on the inside of the tube. And you can actually measure to see how high the mercury raises or rises and falls, depending on the pressure, how much the air is pushing down on the outside or not pushing down on the outside. Those are the early barometers. So our barometers today work kind of like the same idea for it, but we don't use the mercury barometers as much today. Your book points out the greater the atmospheric pressure, the greater the height of the mercury column. And since pressure is force per unit area, the size of your container doesn't matter. As the area increases, the total force in the area also increases, so the pressure is the same. So your book's pointing out that if I were to use a bigger tube of mercury, it would still rise the same amount on the inside because it's dependent on the pressure of the force per unit area, not on the size of the tube. This isn't capillary action, so it doesn't matter if it's a skinny tube or a fat tube. It's the idea if it's the force per unit area. Alright, your book points out as well that that the height of the mercury column in the barometer is not constant. It varies with location on Earth and with weather conditions. So again, thinking back to physical science, if I were to climb to the top of Mount Everest, and we're just going to ignore the fact that it's really cold on Mount Everest, and I'm going to bring up a mercury barometer, that if I were to go higher up in the atmosphere, is there less air pressure around me or more air pressure around me? Alright, hopefully you said less because I'm going higher up in the atmosphere, so there's less gas molecules around me because I'm going higher up in the atmosphere. So since I'm going higher up in the atmosphere, there's less pressure pushing down on my barometer, so my mercury column would actually go down because there's less pressure on the outside pushing it to keep it level. So my mercury would actually go down because there's less pressure at the top of Mount Everest. If I were to go to the Dead Sea, that's the lowest point on land. So if I were to go down there, it's because there's more atmosphere pushing down on me now, and I were to bring my mercury barometer, there's more air pressure. So because of that, the air pressure has increased around me. So the mercury on the inside of my tube would start to rise or go up because the air is pushing harder, and it's basically pushing it down at that point, where it's escaping and going up my tube, because there's more air pressure around me. So that's what it's talking about whenever it says it varies with location, if you're higher or lower in the atmosphere. It also varies with weather conditions. You might hear about meteorologists talking about atmospheres or bars or tours. And that's what they're talking about the pressure around it. Your book points out fair weather is generally accompanied by high atmospheric pressure and stormy weather by a low pressure. You might be wondering, okay, if I have atmospheric pressure, why does it matter with saying where's the gas or where's the air coming from? Alright, so if I have high pressure, if there is a lot of pressure in the air around me, so it's a high region of pressure, my mercury column will go up or go down because there's a lot of atmospheric pressure around it. Hopefully you said, okay, so there's a lot of pressure pushing down on it, the mercury column will start to rise or go up. Alright, now thinking about it with storms, does air want to move to where it wants to be close together, because it's a gas, or does it want to spread apart? Hopefully you said, okay, gases want to spread apart from each other as much as possible. So if I have a high pressure region or a lot of air, gas in one section, a lot of wind, they don't want to move to that section, they want you to move away from it. So so there's no storm coming into the area. If I have a low pressure region, you might remember with meteorologists, if you watch the weather, you might notice that the meteorologists talk about highs or low pressure regions. So if I have a low pressure region, or there's not a lot of gas or air in the area, it's weaker, so it's a low pressure region. That means with my mercury on the inside of my barometer, will it go up or go down if there's not a lot of air pressure around it? Hopefully you said it'll go down. So scientists or meteorologists know, oh, it's a low pressure region, the barometer is going down. That means that this is an area where there's not a lot of air pressure, there's not a lot of gas in that section. That means since air wants to spread out, and there's an area of low pressure in this particular region, that means that air is going to start moving into this area. So you're going to have wind typically move into that section, and wind in a lot of cases brings storms. That's the reason why scientists will say we have a low pressure and there's storms moving into the area, because the wind is moving to fill in that spot. So that's the reason why. You don't have to know it that detailed. I just wanted you to know so that way you understand what your book's talking about. Alright, so today, instead of using a mercury barometer, you might use an aneroid barometer. Your book has this cut out as well. So an aneroid barometer is a compact and more rugged type of barometer. It has a flexible air-like metal box. So instead of having mercury, because mercury is dangerous, they use basically a flexible diaphragm on the inside that'll shift. So if there's a lot of pressure on the inside, it'll shift, pressure of the atmosphere on the outside, it'll shift inward. If there's less pressure, it'll shift outward. So it's moving and shifting in and out with the container. And it basically tells the pointer on the pointer to shift based on how much it's moving. So you don't know it super in detail. I'm just going to note an aneroid barometer is a flexible airtight metal box. So as the air pressure increases, the metal box flexes in, and whenever there's less atmospheric pressure, it flexes out. Just make a note, aneroid barometer. This one doesn't use mercury. So make a note for that one. Alright, pressure units. So, oops, we'll just go back to this one. So for the pressure units for atmosphere, we do use pascals, but with meteorology, sometimes they will use different pressure units for it. So, although the pascal is the official SI unit of pressure, scientists use several other units as well. Your book has this chart on page 63. You want to know this chart really well, as a side note. So there are three major ones that you need to know. The first one is millimeters of mercury. We use the symbol for it of mmHg. Alright, so hopefully you might recognize this. It's kind of familiar because millimeters and then Hg, remember that the periodic table stands for mercury. So this is literally millimeters of mercury. So this should be really easy to help you to remember. So pressures in millimeters of mercury and mmHg. These are convenient because we look at it with the barometer. So if you're using this one, we can literally measure, see how much is the mercury rising or falling on the inside, and see, okay, it has risen to 753 millimeters of mercury. Now it's gone down to 323 millimeters of mercury. So that's the reason why we use it. So because it is convenient. So it's convenient with mercury barometers and other devices. Oh, like for your book says, like for 50 millimeters of mercury, that's the air pressure. It can support a column of mercury 50 millimeters. So that's easy for it. But because mercury is affected by temperature and strength of gravity, it's not perfectly accurate, but it works good enough for scientists to use it. A torr is named in the honor of Torricelli. So make a note for him that this unit is T-O-R-R. So just make a note of a torr for that one. Now, this one is precisely defined in the terms of the Pascal, but the important thing is that these two units are equal to each other. So if I have 1 millimeter of mercury, I have 1 torr. If I have 760 millimeters of mercury, I have 760 torr. If I have 573 millimeters of mercury, how many torrs do I have? Right, 573. These two units are equal to each other. This one is just defined in the SI system, while this one's not. So that's the major differences between them. Alright, we also use the standard atmosphere, or ATM. I just dropped my chalk, that's sad. So the standard atmosphere, or ATM, so atmospheric pressure, so ATM, I'm going to write it again. So ATM is the abbreviation for it. So that's the standard atmosphere or the standard pressure. It's two different names for the same thing. This is the average air pressure at sea level. So let's make a note for that. This is the average air pressure at sea level. So, to make it up for this one, so 1 ATM, so 1 standard atmosphere, is equal to 760 torrs. And remember, since these two are equal to each other, this is also 760 torr. So, you have 760 torrs at 1 ATM, or 1 standard atmosphere, and since these two are equal to each other, whatever you have of one, you have the other. So, let's make a note for that. So, standard atmosphere, that's just the average air pressure at sea level. So, if you were to go higher up on Mount Everest, so there's less atmosphere above you, you would have a lower pressure. If I were to go to the Dead Sea, because it's lower, there's more atmospheric pressure above me, so that one would have a higher atmospheric pressure. Alright, so your book asks you a couple of questions about it, just pointing out that there's a couple of other ones, like the bar. That one is equal to 10 raised to the 5th powers of Pascal. So typically in meteorology, they'll use a bar or a millibars. You don't have to know that, but do make a note that you want to be able to reference what a torr is, how it relates to millimeters of mercury, and how it relates to atmosphere. We use those all the time. Alright, so let's look at manometers really fast, getting into it. So this is a device that scientists use to measure the pressure of the gases. So there are two types of manometers, an open-ended and a closed-ended. So the open-ended one is open to the atmosphere. For the closed-end one, it's sealed off, so that way it's not open to the atmosphere. So your book has a picture of this device. I'm going to draw it very loosely because I'm not a good drawer. Okay, that's decent. So make sure you can see that. Okay, it shows up. So this is the device where I have my gas sample on the inside. I'm just going to label it gas. Now this is an open-ended manometer. It is open to the atmosphere. So remember, atmosphere is constantly pushing down. So if it's open, that means air is constantly pushing on the inside of it. Now my gas, once scientists open it up, the gas wants to spread out from each other as much as possible. So they want to try to fill up and spread out from each other as much as possible. What they do is they have mercury on the inside of it, and it's attached to a gas sample. And they want to measure to see how much the mercury moves on the inside. This is kind of like a reverse game of tug of war, where you have the gases pushing, trying to escape as much as possible, and then you have the atmosphere pushing back as much as possible. So it's kind of like reverse tug of war. Instead of both of them pulling on an object, they're both pushing. And the stronger one will cause the mercury to shift on the inside of the manometer. So we're going to use my straw to say that this one is the mercury on the inside of it. So if I have my mercury on the inside of this manometer, if it starts off here and the gas is stronger, which direction will it shift? Towards the atmosphere, towards the open end, or towards the gas sample? If the gas is stronger. Well, he said, okay, it would shift more towards the right area, towards the open area, because the gas is stronger, so it's shifting that direction. Typically, the gas is not strong enough to shove the mercury out. That doesn't happen, so don't worry about that. So, let's say, though, that the gas is weaker than the atmospheric pressure. So, if the gas is weaker, what direction will the mercury shift? Right towards the gas sample. Typically, you don't have it pushed inside the gas sample, because as you have to get closer and closer to the gas pressure builds, so it's typically a gas that's not so weak that it will allow the mercury to go on the inside of it. So it'll shift this direction. The scientists will measure to see what's the difference in the two different parts of the mercury from one end to the other, and they'll let them figure out what's the pressure of the gas sample. They can tell what the atmospheric pressure is with a barometer, so that's not what they're worried about. They want to know what's the pressure of my gas. Alright, so your book gives you a kind of different examples for it, so we're going to look at a moving diagram so you can see this a little bit better. I'm just about out of time, but we'll just look at this first one. Looking at this first example, just showing you an open-ended manometer, so they open it up. Alright, so looking at this diagram, which one was stronger than in this case? Hopefully you said, okay, it's the gas, because the gas has pushed the mercury more towards the atmospheric side. This side is stronger than it. Alright, so this particular example, the gas is stronger. So how do you figure this out? Well, scientists know what the atmospheric pressure is, so that's not the problem. They want to know what is the sample of the gas's pressure. So your book points out at the bottom of page 63, it gives you the pressure of the atmosphere. So the pressure of the atmosphere, and they just say, for this example, that it's 760 torr. So it's that standard atmosphere. Now, if the gas is stronger, if the difference in these two heights of mercury, the difference between them is 400 millimeters of mercury, that means that, okay, not only is the gas at least 760 torrs because it's beating the air, it's stronger than the air. So that means if the air pressure is 760 torrs, that means it's automatically already at 760 torrs. But then it pushed it up farther, 400 millimeters of mercury, or 400 torrs, it pushed it up higher than that. So how to figure out the total pressure? Well, hopefully you said, okay, if it's already 760, and then it moved it an additional 400, then I just add these two together, and that'll tell me what the total pressure is. So for this one, it's 1,160 torrs. So that's the answer to this first kind of practice problem. Gives them on the bottom, page 63. So 1,160 torrs, you just add them up together. All right, looking at the second one, it says, okay, what if you have a gas sample where it's weaker? So again, for this one, the mercury shifts towards the left, or towards the gas sample, because it's weaker than the atmosphere. For this one, it says, okay, the atmospheric pressure hasn't changed. It's still 760 torr. But the mercury has shifted over now towards the gas side, and the difference between this height and this height is 450 torrs. And remember, we measured it millimeters of mercury, but since 450 millimeters of mercury is the same as 450 torrs, because the two values are equal to each other. So, if the atmosphere is 760, but it shifted over 450 torrs towards the gas side, so that means that the gas is weaker, how do I figure out what's the pressure of the gas? Alright, for this one, it's just the opposite. You just subtract it. So 760 minus 450, you get 310 torrs. That's how much the pressure for this device. Alright, we'll go ahead and talk about the closed manometers later on. I'm just about out of time, so again, we'll stop there. Alright, your homework for tonight. So go ahead and get out your assignment pads. Your homework for tonight is you're going to answer on page 65 the application number 2, well, 1 and 2. You can do both of them. So application 1 and 2 on page 65, so application 1 and 2. You're also going to read pages 65 through page 67, so just 65 through 67. You're going to answer on page 71 questions 1 and 2. So on page 71, the concept review, questions 1 and 2. So the total homework, you're going to answer on page 65, application 1 and 2, and then on page 71, the concept review 1 and 2. All right, I hope all of you have a great